Okay, so this is the reference that I have been following mostly. This is Grunbaum, Velkeres, Werner, so GDPWW. This is really the paper which, almost the first paper which introduced this idea of repeated measurements and developed this renewal formalism. Okay, so actually, so we wrote a paper in. Okay, so in 2015, we wrote a paper. This is Shravanti Dhar, Shubinoy Dasgupta, and myself, where we also again use the same idea of repeated measurements, but we use sort of a very different approach, and it was like using perturbation theory, we solved the problem. Okay, and so we were actually not aware of this earlier paper, and this is what we. So we used a very different approach, and I'll kind of talk about that approach. Today. Okay, so then there are other papers. There's a large number of papers by Eli Barkai's group, and I'll just write some references which I'll use a bit today. So this is okay. So it's okay. Okay, so today I'll talk a bit about these two papers. I mean, some ideas developed in these two papers. So this is perturbation theory, and this is some way to make the perturbation theory kind of more rigorous. In this paper, this is what we did, and we'll see actually that finally we recover many of the results that you obtain by the renewal approach. Okay, and these two papers again they use the renewal approach. And I'll talk a little bit about some of the interesting results obtained here. So first, let me start with where we stopped yesterday. So yesterday we were discussing like the infinite lattice. Right, and we make repeated measurements and ask the particle starts from here. So we are looking at this problem where the initial state is 0, and we make repeated measurements asking has it arrived at also at 0. Okay, and the dynamics is just I del t is the discrete Laplacian, which means okay, so then we said that, okay, so here we can basically, we just use the standard formalism and find mu of z. and then we find a z. Right. So mu of z, so we said that mu of z is equal to expectation of I. Okay, and so we wrote two different expressions yesterday. So one is just by looking at if we take the first expression, UNI, then this is so this is our system. So basically, we find all the eigenstates and eigenvalues, and then you can just do an spectral expansion. So basically. And e to the power n means basically e to the power minus IES tau n. Right. Okay, so then these eigenstates are just so the eigenstates of this equation are just plane waves. So phi is 1 by. Okay, so if it's a finite lattice, it's 1 by root L. But if it's an infinite lattice, okay, so let's take a finite lattice first. Okay, so then we can write this as 1 over L. So if I is 0, then you just put x equal to 0. So we get sum over S e to the power minus I epsilon. And if you go to the continuum limit, this is 1 by 2 pi. And this we can do this integral. So this is just e to the power minus 2 pi. Bessel function to n. Okay, so therefore this basically becomes okay. So this is one representation, and then we can also write an integral from here. We can just write an integral representation, which is okay. So once we have this so mu z, then so what we want really is the large time behavior. So from mu z or from A at z, we want to pull out the large n behavior. And this means basically we have to look at properties close to z equal to 1, right? So then we said when we discussed the classical case that basically what we can do is replace z by e to the power minus s, and then look at this at small s. So small s means large n, right? So when you put small s, this summation is determined by the large n terms, right? So then we can replace this by an integral. So this so roughly this is zn e to the power minus ns infinity n. Then what we'll do is for large n, the Bessel function has some asymptotic form. So this is okay, so this is for large n. This is the actually. I mean, you should plot this. I mean, last night I was plotting this. It's. I mean, this agrees even in quite small n. Okay, so even though it's supposed to be large n form, it agrees with this even at quite small n. Okay, so now we just put this here and e to the minus ns. Okay, now I mean so can we find the what is the dependence on S? So what we want is the dependence on S, right? So what is the dependence? I mean, see this oscillatory term we can kind of forget. I mean, if you just look at this and this, from this, can we say immediately what is the S dependence? Huh? Root S, okay. Is it root S? So, I mean, you see, these things you should, the way to look is just look at 1 by root S, yeah. So root n. Then you put a s here and root s here, put a s here and divide by s. Now this thing has no, I mean, if I replace ns by some new variable, then there's no s here. So this dependence must be 1 by root s. Okay, so therefore we find that mu goes as 1 by root s. And okay, so then we are almost done. So a hat. Okay, so this is what we have been doing. Which then we call this a tilde s. This will be 1 minus. And so this now we see that this goes as 1 minus c 1 by root s or c some root s. Right. Okay. Now what is how do we find an from here? So there was some trick that we. Huh? Oh really? Oh, oh, then you should say immediately. Yeah, this you did in the random walk, then in the tutorial yesterday. So this is, you just replace ddn by, okay, so this is, and this we discussed a lot in the earlier class. So this is a method, it's called some Tauberian theorem. I mean, you have to be careful while using it, but usually it works. Okay, so this, then this gives you, so you put 1 by n, so this will give you 1 by 2. Okay, so we have got an equal to 1 by 3 by 2. Therefore, the return time distribution. Okay, so I mean, if you so in this paper by this Eli Barkai and all, they look at this integral and do a more careful computation, and they have a so they have some more accurate form. Okay, so this is. So this is again for large n, but the sort of more exact form is. Okay, so okay, so here if you are a bit more careful with this cos and all, you can somehow get this, but the prefactors are a bit difficult. Okay. Uh, okay, so this result actually will also derive using the other method that I will talk about, this non-Hermitian method. So we'll actually find that we can exactly get this, okay, by a completely different method. Okay, so that is this. Okay, one other thing maybe I thought I will quickly discuss is I mentioned something about yesterday about the this analytic structure of this function a of z. Okay, so I had said that in particular on this unit circle, this function a hat z mod square is 1, right? So there's actually a very simple way of proving this, which I thought I'll just tell you. Okay, so basically what we know is, so we have mu of z. This is given by basically, and then if you, so basically, see this, what I'm going to say is very general, like any Hamiltonian and any initial state, it's a many body system, doesn't matter. This is completely general. Okay, so again, what I'll do, I'll just put a complete set of states and then I'll get sum over S, I. Okay, so now let's call this this thing as PS. So this is sum over S. This, okay. So this CS is basically this amplitude square, and it satisfies the property that sum over CS is 1. Right, that's just from completeness. Okay. So here we are summing over S, let's say all the states, right? So whatever the Hilbert space dimension, so I'll just call it B. Okay, so this is from completeness. If instead we had I and F, then this would be what? This would be 0. Okay, so that it's a bit different. So we'll stick with I and I. Okay, so now this is here. So we have so what is A hat is mu. Okay, so so let's look at mu minus 1. So mu at minus 1 is the, minus 1, but minus 1 I'll replace 1 by this object. Okay, so then this becomes minus CS. So if we take CS common, then it's okay. So now if you just subtract, so 1 goes away, so this becomes CS. Yes, Z. Okay, so we can take out the Z, and so then this is Z. Okay, so therefore, so this is mu minus 1, so therefore A. Okay, so now if you evaluate this on for on the unit circle, which means z star equal to 1 by z, then you can easily see that this will be exactly 1. Okay, so if you just write this into star of this, you can easily see that this is exactly, I mean, this will actually cancel. Okay, so right, yeah. So this is the proof that this is always 1, which means, okay, so sometimes there might be cases where something vanishes and so on. So then it's a bit special. But let's say the spectrum is degenerate, non-degenerate and doesn't vanish, and so the amplitudes are all non-zero. Then it's exactly 1, which means that we showed that the first return first return probability is given by an mod square equals to this integral, right? A hat. Uh, okay, so this means that the probability is definitely 1. It proves that this is 1. And using this, we also proved something else, that the mean return time has to be an integer. So all those things just follow from this very basic rule. The other thing that is also interesting is, which has been discussed in many of these papers, is that I mean, so finally we have some polynomial divided by polynomial, and you want to know like what are the poles of the polynomial. Okay, so that to find that is one thing you can show is, for example, all the poles lie outside the unit circle. Okay, so that there is a very simple proof. Basically, supposing you ask what are the zeros of this function. Okay, so the zeros of this function. So at what values of z is this 0? Okay, so this has a very simple interpretation. This equation, you can just think of like a 2D problem with charges. Okay, so let's say you have these are in the complex plane. This give you the positions of, let's say, some charges on a circle. Okay, so they are placed at various points. So there are d number of charges on a unit circle, and the values of the charges are C1, C2, and so on. Okay, now if you ask what is the electric field at some point Z, okay, then this is exactly the electric field, right? It's 1 over distance. So in 2D, this is the electric field. So this is basically gives you the electric field due to a set of charges on this unit circle. Okay, so now you are trying to find what are the points where the electric field vanishes. Okay, so this equation you can interpret it that way. And then you immediately know that just from physics, you know that it has to be at the inside, right? It can't be, you can't have stationary points outside because all the charges are positive. So you can't have points where the electric field vanishes outside. Right? It has to be inside. So therefore, all the poles have to be inside this circle. Okay, and then you can show that this one is actually the poles are of the zeros of this equation are just inverse of the zeros of this. Okay, so which means they will all be outside. Okay, so this is so there's using this electrostatic analogy. There are several other results you can derive, which was first also discussed in the CMP paper, but then this Barkai and they have done a lot of things using this analogy. Okay, any questions? Okay, so now we'll go to this non-Hermitian description, which is Okay, so again, so this is again, this approach is quite general. It can be used for any quantum system, but we'll discuss it in the context of just the this 1D random walk and 1D Schrodinger evolution. And we'll consider the case where the lattice, let's say, goes uh, from infinity. Okay, yeah. So it goes from 0, 1 to infinity. Okay, so it's the half lattice, and we want to consider the case where the initial state is x. So I equals to x, and the final you want to ask when does it arrive for the first time at the origin. Right? Okay, so and there's nothing on this side. Okay, so this it just makes things simpler, and the equation is still exactly this everywhere. Okay, but now the initial condition is, let's say, okay, let's call it y. Okay, and now we forget this generating function approach. Okay, so now what we'll do is, okay, so what we saw is, let's say we are interested in the survival probability after n steps. So the measurement operator here is 0 and q hat is. Okay, so one thing to note is that the initial state is always somewhere, is not at the origin, it's away from the origin, which means that if I act with q hat on the initial state, then it's unchanged. Okay, so now what we had seen earlier is that the effective evolution of the system is, we can write it as, let's say, psi n tilde is given by u tilde to the power n psi naught, right? This is what we saw. And where u tilde is okay, so things like survival probability at n was exactly given by the norm of this. So this is not normalized anyway because this is not unitary. So the survival probability was given by the norm of this vector. And so if we understand this dynamics, then pretty much we can compute everything, right? Okay, so now what we'll do is, okay, and so we'll try to write actually a Schrodinger equation for this thing. Okay, so how does it change from time t to n plus 1? And then we want to write a continuous equation for something like del t of psi tilde. Okay, so which we will define as like psi tilde maybe n plus 1 minus psi. Okay, so this new notation is getting very confusing because here I put x and then I'm writing n is time, right? Okay, so we want to do something like this. First, write the discrete dynamics, then take some continuum limit. We know there's going to be some problem because of the Zeno effect. If continuous measurement, there will be some problem. So we have to somehow see what to do with that. Okay, so basically first let's just evolve from time n plus 1 equals to okay, so now here we had used, so this was, we had written it as Q U, but now so what I said is that since Q psi naught is psi naught, so we can actually, if we put a Q here, it doesn't matter, okay, because we are looking at the space of the, not excluding the zero. So if we put a Q psi n, it doesn't matter. Okay, it's the same object. Okay, so we'll actually now look at this operator Q U Q. Okay, I hope this is clear, right? Okay, so let's look at this object. So, and what we want, okay, so okay, so basically what we want now is to do some expansion in time, like in the small parameter tau. Right? So the in one evolution. Okay, so this is given by Q e to the power minus I H tau Q. So this is this object. And what is H? So H is H is, so we'll say now H will divide it into two parts. One is the kind of system part, and the one is this is the detector kind of thing. Okay, so we'll write it H in the form following form. So the full H total, let's say, or H is given by sum over okay, so let's say we break this up into two parts. X equal to yeah, 1 to infinity, so 1, yeah, okay, 1 to infinity, and then the remaining part, which between 0 and 1, we write it as okay, and here we introduce some parameter gamma. Okay, so between all these sides, the hopping amplitude is 1. Between these two sides is, let's say, some gamma. Right? So this transition amplitude is gamma, and everywhere it's 1. Okay, so this one will call H system, and this one will call H system detector. Okay, so now we'll write this as and then let's do a expansion. Okay, so since finally we want to divide by tau, so we'll do an expansion till order tau square. Okay, so then this is Q U Q. Okay, is equal to. Okay, so then the order tau cube terms, and then q here. Okay, so now basically what we'll see is that, so what is, if you look at q, h is q, uh, uh, okay, so q has stuff only in this part, right? So q is basically sum over x not equal to 0, right? So it's just the identity on the, so therefore, and hs is starts from 1, right? So basically, as far as hs is concerned, this q is like identity. Okay, so this will just be hs. Okay, on the other hand, if you look at q, h, s, t, q, this is actually, so hsd. So if you put q and q here, q has only terms like this, right? X goes from 1 to 1 to infinity. So clearly this will be 0, right? So this is the projector on the other part. So since this has 0, so this will be 0. Okay, then let's look at these terms. So again, there are various terms. So q, hs square, q, this will be again hs square. And then we have these other terms which are q. Okay, so this also you can see it's 0 because when hd acts on q, it will be 0. And then q acting on hd is also 0. Okay, so this is also 0. So the only non-zero term is basically this q. Okay, so let's evaluate this. So this is equal to hsd square means, so this is hsd. Okay, so when we take square and then sandwich between q, the only term that will survive is basically when we take square, we'll have something like maybe 1, 0, 0, 1, right? And yeah, that's the only term that will survive. Okay, so I hope this is clear. I mean, so we have things like 0, 0, so square of this. So that means I have one more thing. And then on the left-hand side, I have this object. Okay, so x starts from 1 to infinity. So the only way I can not get non-zero is from this into this term. And when I do that, I'll basically get then what? I'll get 1, 1. Okay, so this is basically equal to 1, 1. Okay, so now if I write it out, tau equals to, so we have 1. Okay, so basically psi of so there's a tau here. And then and then this term, right? So this will be minus. Okay, so there was a gamma amplitude here, so there should be gamma here. Maybe gamma square. So minus gamma square. cos square by 2. Right. Okay. So, and then of course, higher order terms in tau and so on. Now, if I if I take this and divide by tau, I get del t psi. So del t psi equals to, okay, so this first term, of course, if I divide by tau, it's all good. So, okay, this term will, if I divide by tau, it goes away, right? So this term goes away, and this term, let's keep it. Okay, so now you can see that if you take tau going to zero limit and do nothing else, then this goes away, and what we get is just this unitary evolution. Okay, but this unitary evolution is now in just this part. Okay, it's just from 1 to infinity. So so the dynamics, the system just evolves out here unitarily, and you'll never detect it here. So this is the Zeno effect. Okay, so now we don't want that. Okay, so I mean, so you can just imagine that, okay, so there are two ways to think about it. One is you could imagine that this, we can still use this approach if tau is strictly not going to zero, but some very small number, okay. So then we can just keep this like it's a perturbative way of doing it. And then you can extract many things. That's the approach that we followed in that 2015 paper. The other way to make it more kind of rigorous is to say that we take a special limit where this gamma goes to infinity, tau goes to zero, keeping this finite. Okay. So this is what we'll now do. So I think this is the factor of 2. Okay, so we'll take the limit tau going to zero, gamma going to infinity, which means gamma is scales as 1 by square root tau. Okay, so this scaling is actually very common. I mean, even if you want to derive things like Lindblad equation and so on using this environment coupling and all, this is the standard procedure. You have to take gamma as scales as 1 by root tau. Okay, so we'll take this limit. Keeping this constant, and let's call this alpha. Right. Okay. So now then we have minus IHS and then some new term in the Hamiltonian, and it's clear that since there's no I, this is a kind of a non-Hermitian term. Right? Okay. So let's write this term now. Let's write this equation more carefully. Okay. So what do we have? So now we have, so we can put a I back there. So we'll get I del P psi, okay. Okay, so you should remember that this psi is different from the original. I think at some point I was calling it psi tilde. So let's call it, so this is it's a normalized state. Okay, so it's a different. So this is the effective dynamics now, which is Hs psi tilde plus where Hs is just the usual this. Okay, so this is the non-Hermitian Hamiltonian basically, right? So okay, because there's an imaginary thing. Okay, so now you can quickly check, for example, that so usually if you work with unitary evolution, you can show that psi will be zero, right? The norm is preserved. So so here, if you try to do the same computation, what is del t of psi tilde? This okay, so I mean, you can. This is a very simple calculation. I won't do it. So you can work it out, and what we'll find is that this decays, and the decay rate is alpha square. Uh, okay, 2 alpha square. Okay, so this is the decay rate. Okay, so okay, so this is very similar to what we had got with this absorbing boundaries, right? If we have an absorbing boundary, then we found that the total probability of the particle being here, that decayed. So this is the survival probability. The survival probability is decaying at some rate. And then, of course, this is equal to, so how is this related to the first arrival time? This is just minus P1T, right? Okay, so for Brownian motion, we had seen that the survival probability, I mean, is basically the current out here, and then this was the first arrival time. And the current had some expression which almost looked like this. Okay, so this approach is in some sense very similar to the absorbing boundary conditions in for random walks, and this has some advantages now, as we'll see, that you can work things out analytically. Okay, because we have to just solve some boundary value problem. Okay, so a few other things that's now that you should notice is that now our space has one less site, right? So the site 0 is gone. The site where we are arriving is gone. This is again similar to absorbing boundaries, where the probability vanishes at the site we want to arrive, right? So it's very similar. So now the dynamics is in just the in the complementary space. Okay, questions? Yeah. Uh, no, so okay, so the reason I introduced this gamma is so that I can do this limit, right? If I didn't have this gamma, then then there's no way I can keep it finite. Okay, so now like what I said earlier is that you can take a different approach where if supposing you just put gamma 1, okay, then of course this tau is there. You can't take tau going to 0, doesn't make, but still you can, supposing you just solve this equation, okay, and you can get things. So that would be like doing perturbation theory. And it will actually be very accurate. I mean, it's surprisingly accurate. Even if tau is kind of large, it's very accurate. But if you want to strictly do things mathematically rigorous, then you have to introduce this extra parameter, and then you have to take this kind of limits. Okay, but you can imagine that I mean, this is, you have some, there's a detector here. So, I mean, there should be some coupling parameter, right? So like physically, it makes some sense. Like there's some parameter, and you want to detect where you want very good, strong coupling and so on. So maybe there's some physical intuition why you want to do this. Okay, any other questions? In the survival, yeah, like that cos square thing was there, right? Yeah. Yeah, which you would never get in, I think, classical systems. Maybe you can, if you have. Yeah, right, yeah, yeah. Exactly, right, yeah. Okay. Okay, so now we want to basically, let's try to solve this equation, right? So we have to solve what? We have to solve uh, okay, so okay, so this is the equation we want to solve. Uh, x goes from and x goes from 1 to infinity. Okay, so here we have to also introduce one boundary condition because there's no psi 0, right? So we have to say psi 0 is equal to 0, okay, because there's no psi 0. Okay, so this is the equation we want to solve, and we want to solve with the initial condition that psi takes at. And once we solve, then if we can find, for example, psi 1 t, okay, so this is all tilde. Okay, so I mean, I'm dropping the tilde for now. Okay, so if we can solve this equation, and then we just need psi 1 t at site 1, then we can find everything. Right? Okay, so let's see how to solve this equation. Okay, time. Okay, so what we'll do is, okay, so so it's a linear equation, of course, and there are two ways to solve. Okay, maybe there are more ways, but one standard way is would be to find the spectrum of this. Okay, so its spectrum would be slightly complicated because there is a kind of defect at this at the first site, right? So it's a bit complicated. So we'll use a slightly different approach. So in our paper, we actually solve it using both these methods, but I'll discuss this other method, which is just first take a Laplace transform. Okay, so we just take a Laplace transform of this equation, which is multiplied by to the power minus st, and take uh, okay, so if we do that, what we'll get is, so e to the minus st, so you have to do some partial integration, and we'll get I. Okay, I'll call it the uh, so I'll use the notation psi x hat for Laplace transform, right? And this is now a function of s. Okay, so this will be hat at s. Okay, so I mean, so basically I'm doing it multiplying by e to the minus st, and then I have to take del. I can do a integration by parts, so that's why I'll get these two parts, right? Okay, so then this on the right hand side is just Okay, and then what we'll do is we'll expand this in some known basis. So if we didn't have this term, then the eigenfunctions of this system are given by, okay, so, okay, so for, okay, so this spectrum is simple. So this is just given by the eigenfunctions are phi, yes, not S, maybe alpha. And okay, so Q is because it's the positive half, Q is not minus pi to pi, but 0 to pi. And okay, so these are the eigenstates, and the eigenvalues will be epsilon Q equal to, so just from here it's clear that it's 2, 1 minus cos Q. Okay, so now we will now expand basically psi xt in this basis. So this is given by psi. Okay, now let's put here q, and okay, here maybe I'll use tilde. Tilde t. Okay, so this is the Fourier expansion coefficients, and the inverse is given by psi q tilde t. Okay, so this, so I can expand the, I can, since this forms a complete basis, I can expand the solution in this basis, right? This is the inverse of the. Okay, so now we'll just use this transformation in this equation and try to see what are the, and try to determine the, in the Fourier space. Right, so basically we are doing kind of Fourier Laplace transform. Okay, so if we do that, okay, so so the first term will be, okay, why is there I here? Okay, so the so when we take Fourier transform, the first term will be, okay, this is time. This is time is 0, and this is space. So we'll get phi psi hat q at 0. Okay, so we'll get I psi hat. Is it hat or? What is that? Okay, I mean, I think I'm mixing up notation. So we're using Fourier transform. So the Fourier is called tilde. Okay, so just tell me if I'm making some mistake. Plus in notation is. Okay, maybe let me do it there because otherwise I'm getting mixed up. Okay, so the And basically, we are multiplying this by phi qx and summing over all x. So then the first term is phi, and our notation is psi q hat. So I 0. Difficult to, okay, so this one we use the fact that it's an eigenstate, so this will be given epsilon q alpha psi 1 hat. And this one let's keep phi q. Okay, there is psi tilde. Okay, so I hope this is clear. Maybe this should be this hat. This I one hat. Okay. Yeah, so this last term, this is okay. So this index 1 is site 1. Okay, there's no x here. So if we multiply by phi q, so what we are doing is multiplying by phi qx and summing over x. So we just get x equal to 1. So phi q1. Okay, but this one will still remain like this. And this is this 1 means at site 1. So it's still not in q space, right? It's still in real space 1. But this hat means Laplace transform. Okay, so this is what we, so now we can solve this to find psi q hat s. Okay, there are still some things known. Okay, so this one we know because this depends on initial condition. And this is from here, if we put t equal to 0, so psi x at t equal to 0 is, we said delta xy. So we'll just get phi q at y. Okay. So this thing is just depends on initial condition. So this is equal to phi q at y. Okay. So then this is still unknown, but we can, let's solve this equation for psi q hat. So so then we get we bring it this side, and we get psi hat tilde. Okay, let's put here I. So I will here, so we get I. Okay, so now okay, so this is still unknown. So what we know is that psi, so this is site 1. So psi 1 hat S should be given, so psi 1, this is in Laplace, yeah. So psi 1, if we do Laplace transform, so psi 1 hat S would be psi q tilde hat S, this phi qx, phi q at site 1. Right? So from there, psi 1 hat S is sum over x, no, sum over q. Where is this sum over? Okay, so I think I've okay, there's something obviously wrong here. No one said anything, but this is obviously wrong, right? This should be integral. I mean, because q is continuous 0 to pi, and this should be sum. Okay, right. So psi 1 hat S is not is an integral dq 0 to pi. Okay, so so now what we can do is we can get an equation for psi 1 hat by using this fact. Okay, so we already have some expression for psi q which involves psi 1 hat, but now we can use this other equation. So basically, supposing we take this, right, and multiply by phi q1 and integrate over q. Okay, so if we do that, this will give what? It will give psi 1 hat. Okay, so we are multiplying by phi q1 and then integrate over q. Okay, so then this gives exactly psi 1 hat s, and this is equal to, okay, so here we have something. So the first term is I integral over dq 0 to pi. So we are multiplying by phi q1. So this is phi q1 phi qy divided by q. And then here the next term is minus I alpha. So this is still the same. There's no q here. Okay, then we have dq. Okay, so now therefore we have an explicit solution for psi 1 hat s, right? We can just take it this side, and we have an explicit solution. Okay, so solve for so psi 1 hat s is then just I. 1 plus, so I'm taking with the set, so it's 1 plus I alpha. Okay, so we have some very explicit form, right? So this phi q is just sine q and phi qy sine qy. Epsilon q is 2, 1 minus cos q. So we just have to do these integrals. So if you look at it, actually this looks very similar to what we got from the renewal approach. Okay, there was something divided by something, so it's actually very similar. And yeah, so maybe somehow you can, I mean, so this looks very similar to mu of z maybe, okay, or not mu of z, in fact b hat of z, okay, which was the renewal equation for z y to 0. Okay, so anyway, now the good thing is that one can actually explicitly do these integrals, okay, because here this is cos q, so you can just do contour integrals, you can do all this exactly, okay. Okay, so in our paper we have the exact form which I won't write, okay, I could write, but maybe I won't write. Okay, so what does this give us, right? So, so this can be done exactly. Can be, maybe what I should say, integrals can be computed. Okay, so this is, if you remember, this is basically psi at site 1 t. Okay, so this was just the Laplace transform, right? And earlier we said that if we know psi 1 at time t, from that we can find everything. Like the first passage time distribution is given by p1t equals to it was basically minus 2 alpha psi 1 t square. Right? So if we know, if we can invert this, then we know this exactly. Okay. So okay, so this first of all we can find this explicitly, and then we can also do the inverse Laplace transform. So psi 1 t is okay. So some contour integral, right, e to the power s t. Some contour. Okay, so okay, so we have some actually we can find some series form, and from that if we work it out, the leading form is okay. So if we erase that part, so from the renewal approach, I said that this Eli Barkai et al. They calculated this form, which is cos square. Okay, so there's some pi n cube. And so from here, I mean, so I won't do the details, but you can work this out exactly, this inverse transformation. And we find also we can get exactly that result. Okay. Okay, so what else can we do? So the one other nice thing that we can do from here is find the survival probability. Okay, so if you know this asymptotics, then of course it doesn't tell us what is the survival probability, right? Because the survival probability is an integral over n from all times. Okay. So the survival probability is basically s of t is yeah, it's this integral p1 0 to infinity, and huh? Oh, sorry, this is S infinity. No, this is, oh, it should be 1 minus, right? This is survival means it doesn't come back. It doesn't ever come to the origin. So this is the probability it doesn't come back. Yeah, so this is 1 minus E. Okay, so now this P1T is, so this is psi1 mod square. And so psi1 mod square will be, so this we can write it as in terms of the Laplace transform. Okay, so if you do a Laplace transform, this will be psi1 hat is okay. So basically, you can write this integral this is 0 to infinity in terms of the Laplace transform, okay, which we know very explicitly. Okay, so now it turns out that you can actually do this contour integral also. Okay, so this I had this really amazing student Varun Dubey who was really good at. I mean, it's not a simple integral, but he could somehow do this exactly. And so we have a closed form expression for the survival probability in this problem. Okay, so then you can ask various questions like, I mean, so what we in the paper we plot it as a function of various parameters like tau and like the position from where it starts. So there are a lot of interesting things that you see in this survival probability as a function of various parameters. So of course, with some finite probability, it survives. It's never, I mean, it won't, so the probability of coming to the origin is not 1, unlike the random walk. It's always less than 1. Okay. Okay, so I think I've like this is the approach using the non-Hermitian Hamiltonian, and again it's very general. Okay, so you can like work with any quantum system, but you have to introduce the system detector coupling, and then take this limit of coupling going scaling as 1 by root tau. To get this non-Hermitian description. Okay, so is there anything else I should say? Okay, no, so I think that's all. So I'll just take questions if there are. Yeah. No, see, finally, it's the other approach was renewal approach, but it's also non-Hermitian because I was still dealing with this non-Hermitian operator, right? It's just a different technique, but of course, non-Hermiticity is there in both approaches. So that's why I mean, everything is the same. So they should give the same result, except of course, here I'm doing this special limit. Like what I said was, if you didn't do this limit, if you just treated this as a perturbation theory, then also it works quite well. Okay, I mean it works remarkably well. I mean if you compare with like exact numerics and this perturbation theory, even if tau is like 0.5, it's very good. Okay, so this of course happens quite often in physics, right? Perturbation theory is extremely good. Okay, yeah. So that's any other question? Okay, so then we stop. That's the end of the class.